Okay, so let's start. Before I start, I have a question. So I see that almost all of you have laptops open. I hope it's not Snapchat, Instagram, Facebook, but rather. So what are you doing with the laptops? Yes, looking at the lecture notes. Okay, there's one. Who does not have a laptop? Raise your hand. I want to see. Get it. Using one here. Who does not have a phone here? One. Okay. The reason I'm asking is because I'm considering moving the quizzes to here. Or at least some sample of the quizzes here. And I see that you're all connected, so with one exception wouldn't be a problem. And this is an in principle exception or just today an exception?
Just today.
Just today, okay, so there's no exception. Okay, so I'll still think about it. If people have strong views one way or another, let me know. Let's start with this. So given that there's no more waiting list because the most of the stuff, drop date actually is still on, but the rest is not. I got some questions on that. So people that are still interested in the class and are not in the class, now it's a good time to petition because we'll have room. So if you're one of these or you know someone who is, let them know. Similarly, for section switches, 419, 519. It turns out that I was wrong last time. The right way to do it now, given that we passed the deadlines, is to a petition. Should be very easy. So go to Levine 309 and get the petition forms. Two other things, my office hours have moved for this week. Just a reminder. And homework one will be released today. I highly recommend that you don't wait. And it's due in 2 weeks. I highly recommend that you don't wait 2 weeks or not even 10 days, but rather start as soon as you can. Ask questions. I think it should be completely debugged and completely clear. I also ask the TAs not to respond to your Piazza's questions immediately, unless there is some clarification that it's easy and important, because I want you guys to respond. Hasn't been working so far, but let's see. So I'm hoping that you will respond to questions that other students have, and we will start responding only a few days later. Questions? No questions. Okay, so we're talking about decision trees. And we said a few important things. We said that they're very expressive. Specifically, we talked about binary decision trees, and they can represent any Boolean functions. It's useful to think about it as a compression of the data. In fact, almost any learning algorithm is useful to think about it this way, but in the case of decision trees, it's very explicit. We also noted, when we looked at decision trees, that evaluating a decision tree is very easy. If you have a decision tree, you have an example, it's easy to run the example through the decision tree and get a label. So the interesting part, given this decision tree, is how to get it from the data, how to learn it from the data. And that's what we want to do today. So the example that I showed at the end last time, and we're going to play with some part of today, is this one. So the label is, will I play tennis today? Yes, no. We're going to have 4 feature types, and they will have 2 or 3 different values. Outlook, 3 values. outlook equals sunny, overcast, raining, temperature, 3 values, humidity and wind. As I said, plus or minus are the labels, and that's going to be the data. So we have 14 examples, and using these 14 examples, we want to be able to learn a tree. And the question is the algorithm, right? So we already suggested last time, some of you had ideas, that the right way to do it is to recursively build a decision tree top-down. That is, choose a root node, look at these examples that satisfy the root node, each one of the values of the attributes, and for each subset of the data, keep on doing the same thing. Choose a root node, look at the appropriate data, and keep on going down. So basically, we have this algorithm that is conceptually very simple. We have a set of examples, S. Label is the target attribute. In our case, for example, here is yes or no. Attributes is the set of the features. Attributes, we're going to use these interchangeably. And the algorithm that we're going to run is called ID3, one of the most popular decision tree learning algorithms. All of them are very similar. That it takes a set of examples, the set of attributes, and the label. And this is how it goes, as we said. If all the examples are labeled the same, return a single node with this label. Otherwise, choose the attribute. Choose an attribute. Which attribute? One that best classifies this set of examples. And this is where we'll have to think about how to define this best and how to find this best. But assuming that we know how to define it and we know how to find A, then for each possible value of A, we're going to start again. So for example, here we have outlook. We chose outlook. Outlook takes 3 values, sunny, overcast, rain. For the case outlook equal sunny, we're going to learn a new tree, which means we're going to take all the examples that satisfy outlook equal sunny. We're going to denote them S subscript B. This is a new set of examples. And again, if it's empty, we're going to just add a leaf node. And specifically, we're going to label this leaf node with the majority of labels in S. If it's not empty, we're just going to run the algorithm again, this time with S subscript V, set of attributes minus A. We already used A, and the label. Simple algorithm. So one question to make sure we are on the same page. If SV is empty, I could just stop, right? Instead, I chose to do something. I chose to add a leaf node with the common value of the labels in S. Why did I do that? The set is empty. I don't need to do anything. So there's no example with A equal V, right? This is basically what it says. Why do I still bother to do something? Yes?
It's empty in your training data, but you don't necessarily know that in all of it.
Exactly. So remember that all we do now is we use the training data. Tomorrow, when someone gives you an example to run on your decision tree, maybe A equal V will have examples. And you'll have to do something with them. Now, you don't have a lot of information now for what to do with them, but you want to be able to make a decision that is sensible. So at evaluation time, you'll have to be able to do something. So remember always that there There's training time that hopefully you do once, and then most of the lifetime of this decision tree or any hypothesis you learn will be when you actually use it. Okay, so, but you can see yes.
On the ad we showed with the common value of labels, is that the least common value, or like if there's two like different values for labels, for example, is it just choosing the one that's most common? I'm not sure what like common means.
So specifically, count how many positive example and negative examples are there and choose the one that is more common and use it. But in fact, you can do other things. Maybe you're already down the tree, 7 levels down the tree, and you don't want to take the most common in all of S, but maybe in a subset of S that is relevant to you now. So this is just, so you can imagine sensible variations of what I've written here that are more relevant in given context. The key point I wanted to make is that you have to do something here, because otherwise, when you see a new example, you may not know what to do. Okay? So it's a simple algorithm where the key issue is to choose the root tree. And when we think about this, we have to think about what is our goal. So I already mentioned last time, we want a small tree. Why do we want a small tree? Occam's razor's principle that we talked about already a few times, and we haven't justified it. We will justify it a little bit later this semester, but anyway, you will define a minimal decision tree, and there are multiple ways to think about it and define it. The problem is going to be computationally hard. So what exactly is the computationally hard problem? Here is a data set. Here's 100 training examples. Someone tells you there is a decision tree that is small, under your definition of small, that is consistent with this data, find it. That problem is hard, computationally hard. Instead, what we're going to do is we're going to use a greedy heuristics that intuitively does the right thing, does not guarantee optimality. And in this heuristic, as we said, the key decision is the attribute. So back to where we ended last time. We want to develop some intuition for what's the right way to pick the root attribute. So the data that we had last time, I'm sure you remember, we had 2 attributes, A and B. They're Boolean, 0 or 1. We have 50 examples that are 0, 0, and they are all negative. We have 50 examples that are 0, 1. They are all negative. We have 100 examples that are 1, 1, and they are all positive. And the question that we asked is, which attribute do you want to choose first? And last time we got 2 views. Some people thought A, some people thought B. Let's revisit it now and make a suggestions. Yes?
If we have no examples of A equals 1 and B equals 0, then why are we saying that they're negative? Like, could we just say that?
That's for the next slide. Yeah, they're not negative. They're not there. Don't see this slide. Unsee it. But given that you looked carefully at the data, what's your suggestion for the attributes?
So I think we should hinge on A, because if you just look at it in terms of A and forget about B, everywhere as far as we know where A is 1 is positive, and everywhere as far as we know where A is 0 is negative.
So the suggestion here is choose A, and the reason is that if you condition on A, you already know what's happening, right? You don't need to consult B if you know A. Everyone agrees? On the other hand, if you choose B, what's going to happen? Yes?
If B is 1, we have to like check and see what A is.
Exactly. If B is 0, you know, but if B is 1, you still have to ask another question. So structurally, these two trees are going to be different. This is going to be the splitting on A tree. That's it. If it's 0, you know it's negative. If it's 1, you go it's positive. This is going to be the splitting on B tree. And since we want a small tree, easy decision, right? We want to split on A. So let's change it now. And what if we have 3 examples that are A equal 1, B equals 0? So that's why now you can see it again. So I change the data. What do I do now? Which one would you choose as the root attribute? Yes?
B, because automatically B equals 0, then we know that it should be a negative, otherwise.
Okay, so if you choose B, you know that it's going to be negative. Otherwise, you ask. So 1 vote for B. Other suggestions? Yes?
I would argue that the same is true for A, because if you know that A is 0, then it's definitely negative. And in addition to that, even though there are 3 examples, still the overwhelming majority of the A equals 0 examples are negative and A equals 1 are positive.
Okay, so basically what you both are saying is that the structure of the tree is going to be the same, whether you choose A or B. Because if you choose B, and it's 0, you know that it's negative. If it's A, you have to go and ask another question. If it's 1, you have to ask another question. But the same thing happens with A. If it's 0, you know the label. If it's 1, you have to ask another question. So from the structure perspective, they are the same. We don't have any way to decide. But, yes?
It might be more computationally efficient to go with the one on the right because we have 103 examples of A being 1. So we have 100 examples of A being 0, and then on the left it would be only 53.
Right, so I think both of you are saying basically the same thing from different perspectives. So what are we saying? The structure is the same, but if you choose A, for half the data, you know what's happening. And for the second half, you almost know what's happening. On the other hand, if you choose B, only for a quarter of the data, you know what's happening. And for the rest, you don't know. I mean, basically, a third is negative, 2/3 are positive. So another way to think about it is, let's assume you have to run 1,000 examples through this tree. How many questions will you ask in each case? Let's random examples over A and B. And you want to run them through the A tree and the B tree and see how many examples, how many questions you'll have to ask. So that's another perspective, very similar again to the perspectives that you had. So basically, it's a little bit hard now, but both of us, or all of us, hopefully have some intuition here. Yes?
When you say random examples, do you mean that there will be an equal distribution of pluses or minuses, or do you mean that the distribution will be the same as we've already seen?
So that's a good question. When I said random, what I meant was A and B are going to be 0 or 1. The randomness is going to be over the selection of A and B without looking at the labels. You could define random also in another way based on labels. That's what I meant. So basically, I think that the advantage is A, but we really need a way to quantify things. And this is where we'll try to go now. So we're going to try to develop some information theoretic concepts that will allow us to do this. Yes?
Can you explain why is that A would be more advantage? Is it like computationally or is it out of so many data? Like,
So
is it that it will be faster, or is it that just...
we will, on average, we will ask less questions with the A tree than with the B tree.
Is that a weighted average or something? How do we...
No, just think about, so I'm going to quantify this in a second, but just think about running 1,000 examples over this. Think about how many questions you will ask on the A side, right? So in half the cases, you will ask one question. In the second half, you'll ask two questions. On the left one, in a quarter, you will ask one question, and in 3 quarters, you'll ask two questions. You're going to work harder. That's one aspect. So in principle, A, you are closer to the label with the A tree than with the B tree. But we're going to, as I said, develop some ideas from information theory. Specifically, it's going to be called information gain that will allow us to quantify this. There was a question there?
Yeah, I have a question about the previous slide. What if the price of asking A is greater than the price of asking B?
Excellent question. Yeah.
Is there a way of addressing that in this technique?
Yes. So we are going to define information gain. And a few slides down the road, I'm going to say that you can define information gain otherwise to take cost of attributes into account. Yeah. So that certainly is an important question. I'm going to assume now that everything is the same. But definitely, there are many situations. Think about the medical domain, and each attribute is a measurement, and sometimes you want to save measurements because they are costly. You want to take this into account. The way we quantify this is going to be using a notion of entropy. I'm sure everyone heard the word entropy, and now we're going to define this mathematically. So this is a property of a discrete probability distribution. Specifically, if we have a set of examples, we look at the labels, and now we have a distribution over, say, 2 labels in this case. And the entropy of this data set is negative p plus log p plus minus p minus log p minus, where p plus and p minus are the proportions of positive and negative examples, respectively. So let's take the extreme cases. If all the examples belong to the same category, all of them are positive, the entropy that we're going to get is 0. Think a little bit about why. If all the examples are, equally mixed, 0.5, 0.5, then you're going to get negative a half times log of a half minus a half log a half, and you're going to get 1. So basically, you want to think about entropy as the level of uncertainty. If you already know the label, it's positive, or it's negative, then there's no uncertainty, the entropy is 0. If you know nothing about the labels, it's 0.5, 0.5, then the entropy is maximized here, and it's 1. Now, in principle, we can do this with any number of labels. If you have k labels, the entropy of P1 up to Pk, these are fractions, which means that the sum of the pi's is 1. So you can think about it as a discrete probability distribution. It's just sum 1 to k, negative value of pi log pi. So, for example, here are 3 distributions over 2 values. What will be the entropy on the one on your left? Low, high, middle? Low, because I basically know what's happening, right? It's almost all plus. What about the next one? This one is going to be 1, because it's 2 values, and it's exactly the same. And this one is going to be something in the middle. So that's entropy. Now, of course, as I said, I can do this also for k values. And in this case, here is one case, second case, third case. What will be the entropy on the one on the left? Somewhere in the middle. The one on the right, I basically know what it is, right? It's this fourth value, so it's going to be very low. And the one in the middle, what will it be? It's going to be high. Specifically, what will it be? So how many values? What is k here? Let's count. It's 8. So what would the entropy be? If you can quickly compute, this is 8, and this is log 8. And we sum 8 times. Log 8 is going to be 3. Thinking log base 2, computer science, log base 2 always. So it's not 1. 1 is when there are 2 values, but this is the maximal value that you can see. But basically, the principle, it's high when it's uniform. So given this notion of entropy, now we're going to define the notion of information gain. And the information gain is going to be measured per attributes. The information gain of attribute A is the expected reduction in the entropy that is caused by partitioning on this attribute. So I'm starting with a data set S, and I'm looking at its entropy. And then if I'm choosing A takes values V, and I'm going to measure the entropy of each one of the subset and do a weighted sum of them. Right? So SV is going to be the subset of S for which the attribute has value V. So I'm going to compute its entropy and then weight by the size of SV. So again, if I partition with low entropy, which means very imbalanced, if I have a partition for which I actually know what's going to happen, then it's going to give me a high gain because the entropy is going to be low. I already know what's happening. If the partition is balanced, I don't know what's happening, then I'm not going to get a high gain from choosing it. So again, you want to remember, high entropy is high level of uncertainty. Low entropy, there's no uncertainty. OK, so now with this principle, go back to A and B, the previous example that we had, and check whether it makes sense and whether you will still choose A over B. But instead of, you can do it at home. Now we're going to go to our example here and try to see what kind of tree we're going to learn. So what are we going to do? So basically, this is our data. And we're going to consider, oh, you don't see it well here? OK. First of all, the entropy of the data. So we have 14 examples. We have 1, 2, 3, 4, 5 negatives and 9 positives. So the P plus or P minus or P and N are 9 and 5 over 14. This is the entropy of the data. OK? And now what I'm going to do is I'm going to consider each attribute separately, compute the information gain of each attribute, and decide which one to choose as the root. So I'm going to start with this outlook. And for outlook, it takes 3 values. If it's sunny, I'm going to look at sunny here. So sunny has 1 negative, 2 negatives, 3 negatives, positive, and positive. So sunny splits 2 over 5, 3 over 5. So it's very high entropy, right? It's almost in the middle. Overcast, on the other hand, you can see that all the overcasts are positive. Overcast here is positive, overcast, and these two. So I already know what's the entropy. No need to compute. In rainy, I get, again, 3, 2. 3 positives and 2 negative. I know already the entropy. It's exactly the same entropy as here. And now I have to do a weighted average of these, and that's the entropy that I get, which means that's the information gain I got. So I have outlook. Let's take one more example like this. I want to consider humidity. So again, for humidity, if humidity is high, I get 3 and 4, so it's even a higher entropy, closer to a half. If humidity is normal, you can see that it's very extreme. I get only one negative example, so the entropy is somewhere in the middle, and this is the expected entropy and the information gain. That's the game we're playing. Okay? So now I have to do this 4 times. I'm not going to do it here 4 times, but if you were to do it, you would get that these are the information gains of the 4 attributes, which means I'm going to choose outlook. So I'm going to split on outlook. What am I doing now? Now that I split on outlook, I split the data set. Those for which outlook is sunny, I have 5 examples. I'm writing here the indices of these examples. Those for which outlook is overcast, these are example 3, 7, 12, 13, and those for which it's rain. And for each of them, I have to look at the split, compute the entropy, and then compute, again, the information gain. So overcast is very easy because we're done. It's only positive examples. We knew that. But I need to continue on each one of these until either I used all the attributes or I don't have any entropy anymore. So I know what the labels are. So let's just take one example. I'm looking at the case outlook equals sunny. I have 5 examples. And I need to look at each one of the remaining attributes, humidity, temperature, wind, and figure out what's happening. So again, very easy. I'm starting with 0.97, which is my 2-3 split, the entropy of this data set. Right? You can see that I have 2 pluses here and 3 minuses. And then for each value of humidity in this case, I'm looking at the top one here, I need to consider, but in this case it's easy because look at what's happening. If it's high, it's no. If it's normal, it's yes, which means that the entropy is going to be 0. So it's 3/5 0 minus 2/5 0. Okay? Easy to compute. Similarly for temperature. When I'm looking at temperature, I have 3 values, but when it's hot, it's no. When it's mild, I think I replaced wind, weak. Okay, I think I made a mistake here because mild actually splits. So you have to correct this computation here. And similarly for wind. So I have 3 cases. For the case of strong splits between no and yes, and weak splits between no and yes. Hopefully the numbers are correct. So it turns out that what I need to choose here is humidity. That's the highest gain. So I'm going to split on humidity, and you can keep on going and complete the trick. So just to summarize, what have we done? Really a simple learning algorithm. We ask, does S uniquely define the class? If yes, we're done. Otherwise, we find the feature with the most information gain. And then we add children to these attributes for each one of the values. And we're done. Questions on this? Okay, so what have we done? I mean, we basically did a search algorithm, a guided search algorithm, that in principle, in a space that in principle represents all discrete functions. And you're already aware for the pros and cons of this. Pros, why is it good that I did my search in an expressive space that can represent all discrete functions, discrete value functions, yes?
So I guess that means that you know that you have a bounded runtime that's bounded by the total feature space.
Right, so it's finite. That's true. I was thinking more from the perspective of the learning. So why is it good that, in principle, I can reach any possible discrete labeled function, discrete valued function? Yes? So whatever data you'll give me, as complex as it is, there will be a tree there that fits the data. It's a very expressive hypothesis space. So that's the pro, right? It's expressive. If the data is complex, I will still be able to express it with my tree. Cons. Yes?
Yes, because you stop early. Like in the case, in the example, it was like when overcast when it's always yes. You potentially, I guess, lose additional nuance and information which could be given by other features. Like when you evaluate, that could potentially.
But true, but I didn't see any example that forced me to do that. So what are you really saying? Let's.
I guess it doesn't necessarily generalize so well.
So I fit the data, but the con is that I fit the data, right? So maybe I basically fit some coincidental regularities in the data, in the training data, and I will not do well in new previously unobserved examples. So being expressive is good, but it has the disadvantages that I may fit unimportant things in the training data and will not generalize. So we're going to start thinking about this in a more principled way a little bit later today, but it's important to know that there are these pros and cons. So we started at the beginning by saying that we want to find a small or a best decision tree, and this is hard, and therefore we develop these greedy heuristics. And I'm saying here that these greedy heuristics make statistically based decisions using all the data. True or false? Did I make statistically based decisions using all the data? So there are many claims in this sentence. I made statistically based decisions, and I made them using all the data. True or false? You need to help me here. Someone in this area. Yes or no? Yes. Okay, so yes. Yes for what? For the statistically based decisions, or yes for using all the data?
All the data. It was somewhat statistically based.
It's statistically based. I would buy that. You know, entropy driven is statistically based. And yes. But I looked at all the attributes, though. I looked at overcast, and then at temperature, and then at humidity. So I looked at all the data, one attribute at a time, right? So you think we're using all the data. So let's see. So here, how did we compute entropy at the beginning? This is the entropy of the data, right? All the data, 14 examples. And then we split, and this is still all the data. What we look at overcast, at outlook, and we looked at all the data, because all the data have some value for outlook. And then when we went down the tree, what did we do here? We decided, okay, outlook sunny. How did we go from here? Yes?
We only looked at the remaining 3 attributes.
We only looked at 3 attributes, and
We took a subset of the data.
only a subset, only 5 examples here. Well, 5 is a small number, but in general, only those examples that got us to this lead, or to this node in the tree. So we started by looking at all the data. As we go down the tree, we don't look at all the data anymore. So if you think about statistically based decisions, it's a good thing. We want to take statistics over a lot of data because it's more robust. As we go down the tree, our decisions are going to be less and less robust statistically. And this is something to think about, again, from the perspective of generalization. Okay. A small detour to the history. So like all the good things, decision trees were not invented by computer scientists. They were actually invented by psychologists in the 60s as an attempt to model human concept learning. They were then developed in the 70s, late 70s, early 80s, mostly by an Australian guy named Quinlan that developed ID3. And since then continued, and in the 90s and 2000s, improved ID3 various ways into a package that now everyone is using, C4.5 or C5.0, and a few additional bells and whistles. It's been studied a lot by a group of statisticians, Breman, Friedman. They developed something that is called CART, still a book that is worthwhile looking at, CART for classification and regression trees. In fact, Jerry Friedman is still working on these kind of hypotheses. And it used to be one of the most dominant decision learning algorithms. Not the case today, because people understand it very well. There's not a lot to renew or to study in decision trees. It's very well understood, but it's a very, very good algorithm. The most common way people are using it today is not to learn one single decision tree, but rather to use small decision trees and to use them as features in other learning algorithms, boosting, bagging. We're going to talk about this a little bit later. Or the way you're going to use it in your homework, you will also learn multiple decision trees and learn a linear learning algorithm on top of this. So you'll see today when you see the homework, we're going to discuss it a little bit. You can discuss it both in the recitation, and we'll discuss it a little bit next week once you know what it is. But remember that we talked about, when we talked about decision trees, we talked about generalization. So here is a new example that I'm given. Outlook sunny, temperature hot, humidity normal, wind strong, no. So I got this example already after I learned the decision tree. What do I do now? Validate, which means I'm going to check what's happening. So let's check. Outlook is sunny. Okay, I'm going to go here to my left. Humidity is normal. So I'm going to go here to the right. Yes. This one says no. So what do? I have to correct, right? So this tree is not consistent with this data. I'm going to add something. Now it is consistent. Okay? So I fixed the decision tree. Now it's correct. It's consistent with this data. But what is the issue here that could bother you? I can always do this, right? Because I said it's a very expressive class, I can always fit the noise or any irregularities, whether they're important or not. I can fit any data, and I don't want to do it because this is going to lead to overfitting. And this is the key concept I want to address now. So this is our training data. Right? So you see your universe, this is the big rectangle, and inside this big rectangle I have black points and green points, positive and negative example. But this is my instance space. It has a lot more examples. And what I see is a small sample of them, and I'm going to fit this small sample, this one, and maybe that's not what I want to do. So learning a tree, and in general, learning a hypothesis that classifies the training data perfectly may not lead to the best generalization performance. And this is really what we care about, right? Because there could be noise in the training data, and I'm going to fit this noise. And also, the algorithm may make decisions based on very little data. As we said, as we go down the decision tree, we make decisions that are less statistically stable because they are based on very few examples. So we define overfitting in the following way. We're going to say that the hypothesis H overfits the training data if there is another hypothesis, H prime, such that H has smaller error than H prime on the training, but larger error on the test. So you can think about this graph here. As I go to your right, the complexity of the tree goes up. And hopefully, you would agree that that means that the accuracy on my training data goes up. I'm fitting the training data better and better until I completely fit it. But at some point, if you have some set-aside test data, at some point, I may stop improving on this test data. Because now I overfit very specific things in the training data. And this is the point where I would say I start overfitting. And we want to be able to avoid it. So why do we overfit? Too much variance in the training data. So the training data really does not represent the data that we care about. Basically, we split on this last feature that I added in the previous example, features that don't really matter so much. There could be just noise in the data. So what do I mean when I say noise here? You can think about it in two ways. Either, here's an example. The example is good, but someone labeled it plus and should have labeled it minus. Or you can say that my measurement was wrong. So one of the features should have been rainy, but it was sunny. So the feature is wrong. Either way, these examples are noise, and we will learn to predict noise. So in all cases, because what we're trying to do is to minimize this empirical error, the error on the training data, and we can do it with decision trees, maybe what we're doing is hurting generalization. Yes? What do you mean by outliers? So when you say it should be between 100 and 200, you mean one of the features value should be between 100 and 200? Or you're talking about the label?
The label or the value.
Right, so these are the two types of noise I'm talking about, only that I'm doing it in the discrete case. So I have here an example. So I can have two types of noise, and I think outliers are exactly this. So this could have been yes in real life, but someone labeled it no. Or really, when I measured things, I made a mistake when I measured the humidity. It wasn't normal. It was high, but I recorded it as normal. So these are the two types of noise, classification noise or attribute noise, which in some cases people call outliers. It's the same thing. And if I have them, and in many cases I will have them in my training data, and I'm going to try hard to fit the training data, I'm going to learn something that may not generalize well. So what should we do? So in the case of decision tree, yes?
What if you have, let's say, most of the data in one place, and then there's like two that is completely on the other side, but the information about those 2 points is actually correct. So the label is correct, but it's not in the same category as the other data.
So it's really the same thing, because think about the dimensions of this as humidity and outlook, right? So basically what you're saying, all the training data came with very high humidity and outlook sunny, and there are just two examples that have low humidity and outlook, I don't know, cloudy. So basically, again, I'm going to learn what's in the training data. And if eventually the test data is going to be different, it's going to be a problem. Later on, we're going to quantify it as there is a distribution over this instance space. Think about the distribution as some kind of a blanket that goes into your side of the screen, right? So it gives different weights for different examples. My training data is sampled according to this distribution. My test data, hopefully, is also sampled according to this distribution. If that's the case, I'm going to be able to be OK. On the other hand, if there is one blanket that you sample from in training and a completely different blanket that you sample in test, which means in training you'll only see examples from the right side of the screen, and in test only from the left side of the screen, maybe I won't be able to say anything about can I generalize at all. So that's the idea. This is where I'm aiming. Today I'm going to wave my hands around these notions, and later on we're going to be able to develop some better tools. But at this point I'm still algorithmic. So we know something about overfitting. How do we correct our decision trees? So in decision trees, the simple way to do it is by pruning the tree. As we said, the bottom part of the trees is less stable than the top parts of the trees. And what I'm going to do is I'm going to prune. I'm going to remove leaves from the bottom of the tree and assign and replace a small tree at the bottom with one leaf that will assign, say, the majority label to this component. So how do I decide whether I want to do it or not? So I'm going to basically look at some accuracy of my prediction on some validation set. So let's assume I set aside some validation set, and I decide based on this to do it. So really, we can think about two basic approaches. One of them is post-pruning. So I learn the tree all the way, feed the training data, and then I'm going to look at my tree and say, I'm going to remove a few nodes. And I'm going to shorten the tree a little bit so that it will be a little bit more stable. Another way is to do pre-pruning, which is stop growing the tree at some point. So you grow the tree, which means you go down the tree, and you always measure something in terms of quality, perhaps in terms of quality of performance on some set-aside data set that is not being used to learn, but is just being used to measure how well you're doing, so we can think about estimating this performance, the green curve of this graph. And this is how you guide your stopping criteria. And there are multiple ways to guide these stopping criteria. The standard way is to do cross-validation, which means you have a holdout set, and as you go learning, you also measure your performance there and decide. You can think about various statistical tests. You can think about something that is called minimum description length, which is, again, a statistical measure that allows you to decide whether increasing the size gives you something. Is it better to increase the size of the tree or to just keep all these exceptions that you're not using, all these examples from the training as a list on the side and remembering them? So we are going to focus on cross-validation because it's the simplest idea, and conceptually, and think about it as a way to measure the stability of our tree. All these ideas that were developed years ago in the context of decision trees really are related to one important notion of regularization that we're going to generalize later on. Basically, the idea is keep the hypothesis simple, right? So in the case of trees, prune the tree so it will not be too large and too expressive, keep it simple. So why is this important? So I'm going to try now to give you a very brief detour into explaining generalization and overfitting. It will give some intuition for why this regularization idea makes sense. Before I do that, and I'm going to do it in a hand-waving way, yes, so in a few weeks we'll be able to become a little bit more mathematical. Before that, I want you to think a little bit about, okay, so we know how to make decision trees simple. Basically, prune from the bottom. You're running the risk that you're not going to represent all your training data, but the hope is that you'll generalize better. If you were working with linear classifiers, we talked about it last time, what would you do then to regularize? What would that mean in the context of linear classifiers? Any ideas? So here's the example that I have in mind. So think with me. So these are two data sets. Actually, the same data set shown twice. Right? So I have positive examples and negative examples, blue and red. And I can learn this classifier, H2, positive toward the blue, negative toward the other side. I can learn this classifier. Which one is better? Can't hear you. H2 is better. Why is H2 better? Why? I didn't get it. So it has larger gap. There's a larger gap between H2 and the data than H1 and the data. Or another way I can think about it, H2 can help me to fit a thicker separator between the blue and the red than H1 does. Right? And it gives you the intuition that if you can fit a thick separator there, it's going to do better in the future. It's going to generalize better than if you fit a very thin separator. That's basically what you were saying. This is why you preferred H2 over H1, right? Yeah?
Is that the same thing? You have more certainty that this is the right classifier.
So why do you have more certainty? Because you say, perhaps, really this is the training data. In real life, I'm going to get more red points a little bit toward the blue and more blue points a little bit more toward the red. And if I could fit a thick separator, it's still going to do well. It's still going to separate it. If all I fit there is a very thin separator, then when I add these new examples, the red that goes more to the blue side, they're going to cross the separator to the other side, and I'm going to make classification errors. I'm going to assign them the wrong label. So this is another notion of regularization that says thick separators are simpler than thin separators. In what sense are they simpler? One way to think about it is there are a lot less thick separators than thin separators. Think about it. If you have a very, very thin one, you can put many of them between the blue and the red. If you insist on some level of thickness, a lot less will fit there. Maybe you can choose this and this, but not a lot more because they're so thick, they'll cross your data. So this is also a notion of simplicity. Simple is good also in this case. You just have to massage your notion of simplicity in order to convince yourself. Okay, so let's say, so this is an intuition that is really very important. We're going to see this picture a little bit later when we have a little bit more tools and explain it. But now I want to wave my hands around around overfitting and generalization. And I need to introduce some notation. So when we have data, training and test data, we always think about as if there is some probability distribution that governs the generation of the data. This joint probability distribution P of x, comma y, x being the instances, y being the labels. And we are thinking about our data, training and test item, as being sampled from this distribution independently and identically from this distribution. Independently means that the first example that you see was drawn, and then the second one was drawn independently of the first one, and so on. So we have to make these assumptions that training and test are sampled from P of x, y identically and independently, because otherwise no statistical theory is going to help us. And we want to talk about this overfitting thing, right? So a decision tree that overfits the training data when the accuracy on the training data goes up, but the accuracy on the test data goes down. So everyone agrees that this is an appropriate shape for the curves? You would agree that as I grow the size of the tree, I'm going here to your right, the accuracy on the training data should go up. And on the test data, hopefully at the beginning it goes up, but maybe later on will not go up anymore. So you should convince yourself that that makes sense. And this will allow me to talk about overfitting. So I have a notion of empirical error that we talked about. This is the error that I see on the training data, or percentage of items in the training data that are misclassified by my classifier. And I can draw it this way. Yes? No? Makes sense? So I convince you that these are good curves before. Should I convince you that this is a good curve?
This is the test data, right? Not the training data.
I meant that this is the training data. Are you buying it?
If it's the training data, how can an error go get worse?
Yes, exactly. This is this was meant to keep you on your toes, and you should have told me, no, this doesn't make sense. Okay, so thank you. It shouldn't look like this, right? Because as I increase the model complexity, the error on the training data should go down. Okay? So don't believe everything you see here. You have to tell me, doesn't make sense. Okay, good, thank you. What is model complexity? Intuitively, I'm thinking about model complexity as the number of parameters we have to learn, or the size of the tree we have to learn, in the case of decision trees. And I want to be able to think about the relation between this and performance, as we said, on training data, empirical error, and true error or expected error. For the expected error, this actually makes sense, right? Because maybe at the beginning, my expected error goes down, but with time, because I overfit the data with an increase in my model complexity, my expected error will actually go up. Okay, so, but this is really what I care about, right? I care about expected error, generalization. So how can we think about it? So there are two notions that I'm introducing here informally. One of them is the notion of a variance of a learner. And the variance is something that is going to go up as the model complexity goes up. What is variance? Variance means how susceptible is the learner to minor change in the training data. And my claim is that if you have a very complex model, every change in the training data is going to change the model. Think about the extreme cases, okay? In the extreme case, if you have a hypothesis space with one function, change the data all you want, you have the same hypothesis. But if you have many functions in your hypothesis space, you change the data, every blip in the data, you're going to choose another function to fit it better, right? So the variance is going to go up as your model complexity goes up. There is also a more accurate way to think about it, if you want, that I'm writing here with the black font. I'm not going to get into it now, because I want to complete the argument. So this is one complexity parameter, if you want, variance. The second one is bias. And I'm going to argue that the bias goes down with the model complexity. So the more complex the model is, the smaller the bias. By bias, I mean here, how likely is the learner to identify the real target or be very close to the real target hypothesis. And of course, as I increase my complexity, as I'm more expressive, I'm going to be closer to the target function, right? Because I'm more expressive, I can fit all the data. So the larger the hypothesis space, the easiest it is to be close to the target function. Again, take the extreme case. If I have one function, doesn't matter. You can, that's what you have. You have a given error. If you have many, many functions, you can choose the one that is going to minimize your distance from the target function. So the bias is going to go down as your model complexity is higher. And again, we can define this in a more accurate way. In real life, we have both bias and variance. So the bias goes down with model complexity. The variance goes up with model complexity. And the expected error is a function of both of these. And this can be quantified in more accurately. But the key idea is that if you want to have small variance, work with simple models. You're going to suffer from a lot of bias. If you want to have small bias, you want to be close to the target function, work with very expressive models, high model complexity, but then you'll suffer from the variance. And you want to be somewhere in the middle, and this is the region between the overfitting, which I count, it's colored a little bit in blue here that you cannot see, and the yellow-orange that is the underfitting. So we want to be somewhere in the middle between these two. So we want to be able to trade off expressivity of the model with empirical error. as we increase the expressivity, the empirical error is going to go down, but we are running the risk that we will not generalize well. So that's the game that we're playing in learning. And we're going to revisit and see this slide in different ways a few more times later this semester. So we talked about these approaches of avoiding overfitting, and basically that's where I want to end today. So there are a couple more things that I want to say about decision trees, just kind of add some bells and whistles to the basic algorithm, but essentially we covered decision trees. You're going to play with decision trees in your homework, and I want to just finish by asking you to look at the problem set as soon as you can and start working on it so you can I have questions as soon as you can. Okay, have a good weekend.
I have a very brief question. So when you talk about switch section, about the 419 and 519, I'm not really so sure which one I got enrolled to. So should I just check into Pay in Touch and then whatever shows on that, that's the one that I'm enrolled?
I guess so, yeah.
Oh, okay, and the only, because I'm not here for the first week, so the only difference is the project, right?
The only difference is the projects.
Okay, and the members in the project we need to find by ourselves.
I'm going to talk about projects. Yeah, you have to find it yourself. I'm going to talk about it maybe next week already.
Okay, thanks.
In the statement on the slide that said like makes decisions based on statistics and all the data, what was the final, like, is that accurate? Like, again, it's like sequential, right? So it doesn't, like, at each branch, it only takes the data that made it that far, right? So it's not taking all the data again.
It starts with all the data, but as you go down the tree, it uses less data, and therefore it becomes less stable.
So you make that statement, because it reads like an assertion, but it's meant to be evaluated, not to be believed.
Exactly. Okay. So I don't want you to fall asleep. So you have to figure out whether what I'm writing is correct or not.
Okay.
I have a question. You said that with the expressivity of the model increases, then it's more likely to be close to the target function.
Yeah.
What exactly is that?
So you have a hidden function. Let's assume that we don't know what it is.
For the training data?
No.
For
Hidden function.
Okay.
For everything. The training data is some examples that you get as a way for you to learn what is this hidden function.
Right.
Now, in principle, as we said from the beginning of the semester, just by looking at a little bit of training data, it's always going to be very little relative to the whole space of data. You may not be able to find or get closer to the function.
Right.
But if you have very expressive functions, a very expressive function space, you have more chances to be close to the function. If you have very simple class of functions, you will not. So think about the case that, again, is the example that we showed with separating curve that separates the data. It's a very complex function. If I tell you you're only allowed to use linear separators, there's no chance that you will get close to this function.
But if you overfit to all the noise, then wouldn't it be possible that you actually don't get the target function?
But so the issue is that if you have an expressive set of functions, you can overfit. If you don't have an expressive function, it's harder for you to overfit because you cannot express all the subtleties that are showed there. So basically that's the idea. So if you have a lot of functions to choose from, it's easier for you to overfit, but it's also easier for you to fit. Right? You can be close to whatever you want. If you have a simple function, it's harder to overfit, but it's also harder to be close to the true function.
Thank you.
So you said we were comparing thin and thick separators?
Yeah.
And so for the thick one, that just gives you like more space, so if the data point was like pushed a little bit towards like the other one, then it would still fit within your function for the thick one? Or?
So the way I think about it, so you have two data sets, blue and red. Let's assume that your hypothesis class are linear functions with some thickness. And your goal is to fit them. What I'm saying is that if you manage to fit a thick function, you're more likely to generalize better. Really, your function is going to be the one in the middle of this thick. Sure. But you manage to fit a thick one, I'm claiming that you'll be able to generalize better in the future. That's one claim. And the second one was, again, the intuition that thicker separators are simpler than thinner separator from the perspective that there's a lot less thick separator than thin separator. So that's the two intuitions that I wanted to say. Sure.
So just one point of clarification. So say in my training set, there's 5 examples where on sunny and windy days I play tennis, and 5 examples where on sunny and windy days I don't play tennis.
Contradictory examples.
Right, and
excellent.
Not noise, like actual, like these are legitimate examples that we just aren't capturing because the feature space, maybe the feature space isn't robust enough, or
or maybe because you
indecisive.
didn't take one measure that is important, your mood. You didn't. Maybe it's really about mood, but you don't measure that, or you don't put it into your data.
Can a decision tree capture that?
No. You should have asked this question during class.
I didn't know if you had.
I always want more questions. So, if you remember, ask this at the beginning of next time. So this is an excellent example. It shows, first, it's a type of noise, right? Because given the data, the same example appears as plus as minus.
Right.
So it's noise. The decision tree will not know what to do with it. Now you can ask, why is there a noise here? It could either be just noise because someone mislabeled, or there is a reason. There is another feature that we just didn't measure. And this could fall into the notion of missing attributes.
Okay.
Right, which I'm going to mention next time.
Okay. Gotcha.
So yeah, this is an excellent question, and it's a very realistic question. I mean, in real life, you will always
and it makes decision trees, the way that they've been described so far, hard to use in cases where you
decision tree will learn something, and then it will do something with these examples.
Right.
And in some cases, it will label them correctly, and in some it will label them incorrectly. Right. So when you work on the problem set, you will see that you will not get 100% on your data, even though it's clean data. Why don't you? Because your attribute space is missing.
So do we ever move past in decision trees just labels and do percentages of like have a possibility for a label, like 90% sure it's a plus?
You can do that. So you can. So decision trees can be expanded to be regression trees.
Okay.
Where rather than plus minus, you put a real number between 0 and 1.
Right.
Yeah. But the algorithm is basically the same. So there's no point. You have to deal with a few other issues, but basically it's the same algorithm. You still do information gain and so on. So when you look at the package that you'll use in the homework, you will see that they will also have regression trees.
Gotcha. Okay. Awesome. Thank you.
Sure.